Hello and welcome to a discussion of classification. And as I've been doing, it helps to frame these conversations within a context. And in this case, we'll talk about healthcare in particular. So classification unto itself is a technique, and we'll go over what it is, and then we'll talk about an example lifted from healthcare in a well-established data set. So jumping straight in, what is classification? And it's basically a way of determining if a data item belongs to a certain group or not. So in the simplest case, it's a true false. So we decide if an email message is spam or not. So that's a very simplistic case. More complex cases may involve multiple group classification, but in general, it's determining the class of something. So um, generally, we talk about classification as a binary sort of thing a lot of times. So anyway, there are common approaches to addressing it, and it may be that it's around distance. So how close are the things in some measured space? That space may be n-dimensional, meaning that it's not just in 2 or 3 dimensions, but it could be any number of dimensions. We also use things like decision trees to make an attempt to determine what class something belongs to. And we like decision trees because they're pretty understandable. You can look at a decision tree and understand why it did what it did, why the algorithm picked what it did. There's also naive Bayes and neural networks. Those are a bit more interesting, and we'll probably talk about those later on. But for now, we don't need to be too concerned. And in particular, we're going to talk today about the k-nearest neighbor approach to classification. So when we're talking about this, we're going to discuss kind of why you do it and how you might. And in particular, you're likely going to use a library like scikit-learn. And there's kind of 2 methods within that class that are really important when you're doing classification. One of them is fit, and this is essentially where you're training the model. You're giving it some features and some labels and telling it figure out what is the best way of finding these, or how can you classify these items using a k-nearest neighbors approach. And then once you've trained a model, you'll oftentimes use predict to use that model to, given a set of inputs, determine what something belongs to. So we also generally have to do some work with feature engineering, fancy term for basically meaning getting the data to where it can be used for the problem at hand. And that may involve combining together multiple attributes or characteristics or columns of a data set. It may be adjusting them, applying some sort of aggregation to them. So you may take an age and turn it into an age group, and so on. And then there's feature selection, which is given these features, which again, a feature is nothing more than a characteristic. It's an attribute, it's a column of a data set. So not all features are created equal, so to speak. So some features are better than others as far as how well they may impact the ability to predict. So there's a amount of feature value, if you will, that goes with them. And there's fancy names for that. Don't have to worry about it. It's basically whenever you're doing feature engineering and feature evaluation or selection, you're going to want the one that does the best job of helping you, or a collection of them. So when we're doing the k-nearest neighbor classification, the simplest version is that you there's a simple approach. Just take a guess as to how many neighborhoods there may be, and so on. So here you kind of start off, find the ones that are the closest and return the labels that are closest to it. A better way is consider multiple k's. So you start off with k=1, not very valuable. K is the number of neighborhoods within your classifications, how many Ks are there. And then also you want to think about what closest means, and there's lots of variations in general in AI and ML when we talk about closeness. Euclidean distance is still around, even in more advanced things like large language models. Oftentimes, it'll come down to Euclidean distance at the end of it all. There's other forms of calculation of distance, but for now, that's all you need to be concerned with. Whenever you're doing K nearest neighbors, the basic steps that need to be done, and this is very common to not just this particular problem, but in general, we do this. You load your data, you poke around for a bit, you explore it, and then you start taking a look at the attributes and the labels. Then you'll generally split your data into some percentages, either 80-20 or 70-30, or maybe even 5-95. It's going to depend upon lots of factors, including the amount of data that you have. And if you don't have enough data, there's ways to address that as well. We'll talk about them at some point as well. Then you're going to standardize and then fit and transform. Standardization basically means kind of bringing things into the same scale, if you will. So you may make sure that if you've got various attributes, if one attribute goes from 0 to 1,000,000 and another attribute is from 0 to 1, then the larger could impact the model. So you bring them all into the same scale. Generally, it's either 0 to 1 or -1 to +1. Something like that. And then you're going to create a classifier and fit it, which is basically training the model. Then you're going to use that classifier to actually do inference of some form. So you're going to come up with a value based upon some inputs and return it. The reason we do that test train split is that you take one data set, take a piece of it, lock it away somewhere, use the other to do the training and so on, everything you do to it up to that point. And then you're going to get the one that you set aside after you're over to the stage where you're actually trying to start evaluating, right, somewhere in through here. And you'll bring it back and see how well it went. And apologies for that. I hit escape and shouldn't have. So lovely sort of interruption. Bear with me. So back to our discussion. I always forget when I use my little double control thing for my highlighter to just click or something instead, or wait for it to go away. So an example of this whole thing that we may be doing in that checking accuracy is when we're using that test set that we set aside. An example in healthcare is heart disease and applying nearest neighbor to heart disease. This is a well-established problem in data set. So you've got a data set that you get in. It's got some various values, and you'll oftentimes see this is representative of the kind of data you'll see. You may be asking, what is a phallic or a REST CG or ECG or call, I guess it would be, and FBS and so on. And those are the attributes, and they mean things, and you need to know what they mean generally so that you can kind of intuitively see if the results are aligning with what you might think they be. You don't want to go to the point of introducing your own bias, but it's important to understand your data. So in this case, you've got age and years, you've got sex, with male being 1 and female being 0, the type of chest pain. So people describe their pain, if it's angina, if it's atypical angina, and so on. The resting blood pressure, so T-rest, BPS, and the units and it's at the point somebody was admitted to a hospital, so during admission. Your cholesterol, and of course, if you're being admitted to a hospital, generally your blood pressure is going to be up a little bit anyway because you're going to the hospital and you know it's going to cost you. Anyway, you've got cholesterol measured in the units that are supplied and so on. You want to spend your time looking at your data and understanding it. So the fasting blood sugar, important to know. Generally, if it's over, in this case, if it's over 120, then it's high. Otherwise, it's zero. So 120 compared to 100, usually, I guess it's a way of that is kind of for whatever reason, 120 being what's considered high. Your resting EKG or ECG, and if it's the results are zero, if there's a T-wave abnormality, so things like a T-wave inversion. On an EKG, you got your little lines going across, right? So you see it going on TV shows and whatnot, and whatever they do in EKG, there's a whole series of scribbles that you see. There's times when your line should be going down, and it actually is going up, and that's not good. So if it's backwards of what it's supposed to be, then it's an inverted T wave or ST elevation and so on. So and then the 2 is showing that there's a probable or definite some problem with one of the ventricles, and then the maximum heart rate achieved, I would assume that's during a stress test. The exercise-induced angina, so does it happen when they're doing stuff or not? Again, probably from the stress test. If there looks like a ST depression induced by exercise relative to rest, the slope of the peak exercise ST segment back again to the ECG, and then the number of vessels colored with fluoroscopy, so 0 to 3. That means that the blood's flowing through. So you've got something introduced into a dye into your blood. They do imaging, and 0 would not be good, I would think, because that would mean none of them got blood through. That sounds pretty bad. So and then the rest of these, and we'll go ahead and jump in some example graphs that you might see from this, and a few resources if you want to go poke around and look at such things as well. So now to go into kind of the code and a real example, and I'll zoom in a bit here so it's a little more readable. And this code is based upon a previous a previous student's work. So I took a submission and made it pretty, and maybe changed a few things here and there, but to give credit where it's due, it's not with me. So I went ahead and kicked this off. My machine is a little busy at the moment, so it may have taken a little bit to run longer than it should. So anyway, everything should be installed. So this is just importing general libraries. NumPy, Pandas, these are the ones that you will oftentimes use. A plotting library out of Matplotlib, Seaborn are related to the plotting as well, and so on. The last two I probably don't even need because I stuck them in thinking I might, but I don't, because Jupyter is a cool thing. And to take a step back, that's what I'm using, Jupyter Notebooks. It's a very cool environment. It allows you to do this interactive coding where you write code, evaluate it, and get back the results. Also, you can commingle your data with your results and your visualizations and so on. A very popular paradigm for writing code these days. I'm now pulling in the stuff that is specific to kind of this example. We're pulling in neighbors, model selection, and pre-processing from the sklearn, and from that, we're also pulling in some more specific things and doing a little bit of renaming as well. Test train split is such a common thing to do that it is built into the library. So you do it a lot, and because of that, it's already there. It's like baked in because it's important. A helper function that we'll use later on, this will print out our confusion matrix. The confusion matrix is a way of evaluating how well something did, in a particular, how well it did on the predictions and so on. Now I'm going to go out and open up a file. This is the heart disease file, and We'll go ahead and take a brief look at it here and just by displaying it. And so you can see, go back up, these are those names that we went through before. The nice thing with this is you can do a little bit of sorting and whatnot, but I'll go ahead and put it back like it was so that we can kind of see that this is doing a sampling. It's put this 3 dots in. We know there are 302 or 303 rows, 14 columns. These are those columns. Most they all fit. Target would be the thing that we're interested in. So the thing you're trying to predict. So that's kind of that. So going in, and that should have been a let's go ahead and change that to markdown again, breaking down instead of need to be doing, but we'll go ahead and do this live and it may actually make it interesting. Markdown is a simplistic way of displaying things in a way that's similar to HTML, right? That looks a lot like HTML, but yet the Markdown has its own little language. A pound sign is like for headings, a dash is for, as you can see, an unordered list. And so what it's saying here is that we're going to now take a quick look at the data by taking a look at info, describe, and head, similar to what we just did up above with the grid. But whenever we print it out, you can see this is the information about the data we're looking at. So integers for everything except for old peak, the column name, and so on. You'll want to do this generally just to kind of get a sense of your data, in part when you're dealing with things like CSVs, which is what this came in as, right? Way back up here, we did a read CSV on a pandas file, or a file using pandas. And so that read in a CSV. CSVs are a textual representation of data. They don't include things like schemas. So pandas is pretty smart. It took a look at the file, likely did some sampling, although with a small file like this, you can just read it and then take a look and figure out if there's anything in those columns that isn't an integer. It also was smart enough to know that there was a column or a header on this that included the column names, right? So that was very valuable for it to do. And no, I'm looking off to one side, but it's for a reason. Well, anyway, I was looking for this. Is what I was looking for. I was looking for the actual top level Jupyter notebook because I wanted to open up that file, right? So this is the actual, what the text file really looks like. And you can see that's not all that easy to decipher. It's literally a CSV file, right? So, and that's comma separated values. So it's important that you double check the data types and so on, just to make sure it's the right stuff. Describe gives you some descriptive analytics essentially on the data frame. And this is a pandas. These are all pandas data frames functions. So it can tell us the number, the count, and then for each one of the columns, mean, standard deviation, min, the first quartile, the second quartile, and the third, and then the max value for a column. So that's these are important things to know, and in particular, you may want to take a look at things like the mean. The mean in this case was the age of 54 and change. The maximum age was 77, right? So, and the minimum was 29. So somebody was 29 years old, went to the hospital with chest pains or whatnot. Doing those kind of descriptive analytics on sex is pretty meaningless, right? What's the average of the sex? You can kind of tell that there's a bias towards male, right? Just by glancing at the zero, happens to be 0 and 1, and that's sometimes why we do it that way. Anyway, you want to take a look at your data, understand kind of the nature of the data by doing some descriptive analytics on it. So that's something we almost always do. Next, take a look at kind of the first 10 lines, right? What do they look like? And that's similar. If you're doing this at a command prompt using Python interactively, this makes a ton more sense. If you're using Jupyter notebooks to do this sort of analysis, maybe less so, but still, these are the steps we often follow, sometimes just out of habit. And you don't want to attempt to do some sort of classification without doing this. You want to poke around inside of the data set a little bit. Next, we can go in and take a look at the basic, do some stuff so we can plot it out. So you've got to do a little bit of work before we can produce down here, right? So, but when we go to do that, we start off by setting the labels. So female is for 0, and that's what makes this word here show up, right? So we're seeing female because of that. And then male for that one, the CP labels, and these are based upon those descriptions. And this makes the data much more useful, right? So you can actually see that almost half, 47%, was typical, and then 16.5 was atypical, and then 28 doesn't appear to be angina, and 7 and a little over a half was just asymptomatic. So anyway, and then here looking at most people's, greater than 120 at entry, not that many people compared to most were less than or equal to 120. So gives you a pretty good sense of your data. Now to kind of go through how that all works, we talked about the labels, then some counts, and this is basically doing a group by the sex and then getting the counts. Then the CP counts, similar operation. So we're grabbing the column based upon the name out of the data frame, doing a group by that same column, and then counting essentially, or getting the values. And then some pretty colors coming from a nice website for color codes. So you can get a sense of color codes and go pick stuff and get the values in a nice little value, and also be able to see such things, right? So pretty cool. Up here it tells you what you've picked. Nice thing if you're doing any kind of visualization to make things pretty, right? So file that one away, htmlcolorcodes.com. And no, I don't get paid as some sort of commission. Then, so we're basically putting those colors here, and then these are coming in as well. These are just named colors. These are picked because they're different. They're not necessarily named. You could just change it to something else, but that is kind of soothing, right? So now we're doing the actual plotting. So we're going to create some subplots. In this case, there's 3. And 1 row, so you're essentially getting a grid and you're telling it how big it is, and then you're actually plotting the various values as a pie. So each one of these is a pie, and then saving it off as a file, and it's smart enough. Probably this is returning the image that we're actually seeing. So as a result of, say, Fig, this comes back. That means there's also on my inside of the working folder, a picture that was made 3 minutes ago, right? So that was just created. You'll do this sort of thing sometimes because people like to see pretty pictures in PowerPoint and whatnot, right? So we've come to expect visualizations to be built in. Next, we need to do our test train split. In this case, we're doing 25%. So the test is going to be 25, the balance 75 will be in the train. And this function returns back to essentially 4 things, but they're corresponding to X and Y, which is your target and your labels and your values. And so at the end of it all, you also want to do the standardization, and you'll want to do that also, generally speaking, to things that are being used later on. So in this scenario, we're basically training a model and or getting our data sets ready to train the model. But at the point you were to be using a model in, say, a production environment, you want to make sure you're doing the same standardization to the values that are being supplied to it for prediction as you did during the training process. So if you're using a standard scaler during this step, which we're doing right here, you would also want to do that during the actual inference piece, right? So you'd want to make sure you do that as well. So here we start off by doing a grid search approach to finding hyperparameters that are ideal. And in this case, we're looking for the number of neighborhoods, which is K. So the idea of a hyperparameter is, it's a fancy word that just means it's options that have an impact on the training of the model or the framework or the library that's being utilized. So it's a parameter, but it's a hyperparameter, meaning that it's affecting what you get out. It's not just a parameter. So it's a way of being very specific about what it means. And what this does is search the environment, and of course I get an error, which means I didn't run this, right? There we go. So whenever you're talking like I'm talking, make sure you run the code that's necessary to run later on. So all this did up here was generate our sets to show that. We can just take a look and what it looks like. So this is the train for X and the test for X. And we're going ahead and standardizing or scaling our test set as well. So we took it from these various values, and they're all between -1 and +1, right? So in the same, well, roughly, it looks like there's values here. They're in the same sort of scale is the way to say it. We could analyze that data set, but that's kind of off topic. So I printed out something pretty big here, so we'll just scroll on past that. All right, so we're talking about doing a grid search. What this will do is, given this list of Ks, and that's what this is values for that grid search to try out. And we're going to pass it in as a parameter, as in n neighbors, and that's what comes in here. And what we're constructing here is actually a Python object. This is essentially a dictionary with a name and a value, and that value happens to be an array, and the array of numbers from 1, 2, 3, 4, 2, 3, 5, 8, and so on. You could exhaustively search of all of them, so you could create an array from 1 to 100 of all of the values in between. Probably overkill, right? So, and anyway, once you get kind of into the general idea of what is the optimal number of neighbors, neighborhoods, you can do that, right? So, and what we're doing is essentially calling the fit. So we're doing a lot of analytics in that half a second that just executed. And by the way, this is running on a relatively powerful computer. It's not necessarily brand new by any stretch, but it is a fairly high performance machine with things like GPUs and so on, and lots of cores. So anyway, long story short, it's a powerful machine. So there's 8 logical cores with a GPU and so on. Anyway, so it does run pretty fast, but it's not also very much data, like 400 lines, right? So of data, so very fast. So we ran that, and it came back with 21 neighbors is the best as far as this is concerned. And it did some folds here, and so that's a way of so that's what this is. Folding is a way of kind of compensating for not so much data, right? Anyway, so moving on, we're going to actually now go from 5 to 100, right, of neighbors and came back in this case that 16 is the optimal one. So in that case, we did actually go through. Hopefully, this doesn't embarrass me, but if you were to supply 16 as one of these options, you can find it. Interestingly enough, it did before go higher, right? Because I just added that into the possible values up here. It went to 21. That gives you a sense that there's a likely between 16 and 21, a bit of a kind of a local optimal sort of environment, right? So 17 is likely going to be better than 13. Probably 14 is better than 13. But still 21 is close enough, but 16's the better one. You don't generally get the option of doing that sort of thing. That's why you'll oftentimes pick, maybe it's off of every 5 that you might do, or whatever. So we now have our model, and it is trained as a result of this operation here. And so we can take this classifier and now do a prediction against our test set, right? So we got back our predictions for our test set. And then now we're going to go and talk about the accuracy of how well did it do. And it did moderately well. 88% is not bad on accuracy. And then to take a look at the confusion matrix, that lets you know where it got it right. These two are correct, right? So pause a second. Okay, and I'm back. Apologies for the interruption, but that's okay because it looks like my video dropped on me again. So I'll turn it back on. Keeps happening. Some sort of USB thing. Anyway, so not that anybody necessarily wants to see all this, but here I am. So back to confusion matrix, right? So your value is a prediction, so true, false, and in this case it came back that it's supposed to have been true, it was false, so 5 wrong that way. False is down here, so there's 37 that shouldn't be and got it right, but 4 of them should have been false, and we said they were true, that sort of thing. So false, or they weren't false, and we said they were. So this comes down to things like false positives, right? You've heard that expression. So you want to make sure, double check me on that's the way you read the confusion matrix. I haven't looked at it in a minute, so I might have forgotten the actual values. But Google confusion matrix and true positives, false negatives, right? And this is a false positive. So positive, negative, positive, negative. So negatives down here at the bottom, right? That means you actually see the picture better. So that's what a confusion matrix is. The reason that matters is sometimes if you say something is negative and it's really positive, so you said it was negative, but it was really positive, then that can be really bad, especially in the realm of a diagnostic setting. So if I tell you, or either way it can be bad, really. But sometimes it's worse. So if we test you for a disease and I say you don't have it and you really do, that means you're not being treated for it, or you aren't allowing that information to inform your treatment. We'll say it that way. The same thing would be true of the other way around. So if I tell you you've got heart disease and you really don't have heart disease, there's actually an interesting study, and do a little research and you'll find it, where people will sometimes develop conditions that they are diagnosed with. Now, you want to do a lot of research on it, but the long story short, you're bringing in unnecessary stress and you may be undergoing unnecessary treatment, right, because of an invalid test result. An example in my personal life, I recently had a little test done where you wear a sensor on your finger to see if you have apnea or not, or if you have that experience at night. I know I have apnea. I've had it for years. but it came back saying I don't, right, which is problematic. All right, and again, sorry for an interruption. And then the last bit here is we can actually produce a report and talking about precision, recall, F1 score, and so on. Uh, the point of all this is that there are oftentimes multiple ways of evaluating how well something is doing. So each one of those you can research and understand to make sure that you're using the right one, right? So precision is going to be, and this is the distinction between precision and recall, high accuracy, high precision, and so on. So let's go ahead. Then there's the corresponding low accuracy, low precision, high precision and low accuracy. They'd all be together, but not necessarily on the mark, right? So um, anyway, long story short, you'll want to pick. Here we go. Here we go. So the various, this is very precise. Just it's not right. It's not accurate, right? So you'll want them to be both as a general rule. But anyway, so lots of different values, lots of different ways of determining. And so with that, we've talked through heart disease example using k-nearest neighbors. So talked about classification in the context of healthcare. If you have questions, let me know. Like, subscribe as usual. I look forward to your comments if there are any. Stay safe. We'll talk again soon.